So Unit 3 is in our book is called Applications of the Derivative. We've already done some applications like related rates and differentials and such, but what a lot of Unit 3 is going to be focused on is what's called function analysis, okay? So we're going to be looking at some of what we did back in the 2.0 intro to derivative packets. If you remember, we did a whole bunch of like multiple choice and curve sketching and such, where we looked at the relationship between the numerical or algebraic or graphical versions of the derivative, second derivative, increasing, decreasing, all of that kind of stuff. Okay, so 3.1 starts with absolute extrema. It's called global or absolute extrema depending on just the textbook or what worksheet you're looking at, but both of those words mean the same thing. Okay, extrema is the plural for extremum. Okay, so in Latin where the singular is extremum, but really we can just say extreme. In English you do not need to, extreme or extremes for plural, you do not need to use Latin. So our definition for absolute extremes comes from the value of a function at a particular point, okay? And that's an important thing right here, is that when we're talking about a global or an absolute max or min, we are talking about the value or the y-coordinate of the function at a particular point, okay? Frequently when we talk about finding things on a graph, we want to know where things are happening. Where is there a max or a min? Where is there an x-intercept? Where does the function decrease, on what interval, that kind of thing. That's all about the input values. Those are the x coordinates. But when we talk about the absolute or max or absolute min, we are talking about the values. So in other words, we need to be thinking y coordinates. Okay, or whatever variable your output is for a particular function. So if we're talking about a graph of time versus velocity, then velocity, the value of the velocity would be what we're looking at, okay? All right, so f of c, and again, this is a value, okay, this is a function value, is a max on the interval I is just representing an interval here, if f of x is less than or equal to f of c for every x that is in interval I. Okay, so that means for every point that is inside an interval, so let's say our interval goes from A to B, something like this, okay, and I'm just going to kind of make up what happens here. F of c is a max if every other point is less than or equal to that point, or the height of every other point is less than or equal to that point. So in this example right here, since my highest point is happening over here at the end point, then the value right here, so f of b, whatever that is, would be the absolute max, okay? And then f of c is a minimum on the interval if f of x is greater than or equal to f of c for every x in the interval. So if we have a value where everything else is higher than that, so for example, let's say f of, okay, we'll call that point D. Here, let me make this a little bit bigger. Okay, so we'll call that point D, and we'll call this point C. So the heights at both C and D, so this is f of C, which is the same as f of D, since those two heights are less than or equal to there's only one height. Since the height at those 2 points is less than or equal to every other height on the interval, then the value of the function f of c or f of d is the absolute min, okay? Which actually brings up an important point here. The absolute max or min can occur at more than one point if both points have the same height, okay? Because when we're talking about a max or a min, again, we're talking about the value of the function, and a function can still be a function if it doesn't fail any, vertical line tests or anything, if there are two input values that have the same output, okay? All right, so when we think about extrema, we need to think about the possible places where extrema can occur. And there are three that we need to consider for absolute extrema. The first, and these are called critical points, okay? We will need to list critical points as we do these types of problems. So the first is whenever f prime of c equals 0, then x equals c is a critical point. When f prime of c does not exist, so think about something like a cusp or a vertical tangent, something like that, or at endpoints on a closed interval. Okay, so when we list our critical points, these are the three things that we need to consider. Okay, endpoints on a closed interval, places where the derivative equals 0 or doesn't exist. All right, so, and actually there's a technical name for determining the absolute max or min. This is called the candidate test, which really means we list all of the critical points and then we determine which one's the highest and which one's the lowest by looking at the values of the functions at each of those points. Okay. All right, so for this first example, sorry the graph is a little shaky here, but these two do have the same, pretend they have the same height there. They both have a height of 1, okay? This graph has been hand-drawn and then copied and pasted between like 6 different Excel files, so it's a little bumpy looking. Okay, so for this first one, we are looking at a graph. We don't have an equation, that's okay. We still have a function. Okay, and we want to consider all of the places where the derivative equals 0 or does not exist on the interval from 1 to 5. Okay, so the interval is 1 to 5 for reference here. Okay, so first thing I want to do is I want to list any critical points. So places where the derivative equals 0, doesn't exist, or endpoints of the interval. So, or closed interval, which is what we have. So endpoints matter here, so we could say x equals 1 and x equals 5. X equals 2 is a cusp, so that is a place where the derivative does not exist. And then also at x equals 3, the derivative equals 0 because we have a horizontal tangent there. And then actually this entire interval from 4 to 5, so I'm going to put the interval from 4 to 5, actually that's a closed interval because it includes 4. Closed interval from 4 to 5, so we don't need this 5 over here anymore. So all of these are critical points. 1, 2, 3, and then all of the points from 4 to 5 inclusive. Okay? So let's look at the value of the function at each of these. So we'll call this f of x. So f of 1 is equal to 1. F of 2 is equal to 3. F of 3 is equal to 1. And then everything from f of 4 to f of 5 is all equal to 2. So f of 4, and then all the in-between points to f of 5 also equal to 2. Okay, so I'm just making a note here that I'm considering the entire interval. Now, because we are looking at the graph, you might not have to, or you definitely would not have to list all of the critical points, but it doesn't hurt to do this, especially so that when we look back at our notes later, we can see where we got the numbers we got, okay? Okay, so considering all of these values, the lowest value of all of them is a 1. So that means the minimum, the absolute min is 1. Okay, now if a question says where does the absolute min occur, we could say at x equals 1 and x equals 3. Okay, but the absolute min is 1. So if I said how many absolute minima are on this graph, the answer is 1. There's only one minimum because that minimum value is 1. But if I said where does the function attain the absolute min, we could say at 2 places x equals 1 and x equals 3. Okay, so again, I really just want to keep stressing that when we're talking about absolute extrema, we are talking about the value of the functions, not the location. When we talk about relative extrema, which is in the next section, we are going to talk about the x coordinates, the input values, where we get a certain output. So I want to make sure we're differentiating that. Okay, all right, and then for absolute max, the highest value is 3. So the absolute max is at 3. Okay, now just for fun here, let's consider if we were looking at a different interval. Okay, so for example, let's say that our interval, instead of being from 1 to 5, was just from 3 to 5. Okay, if the interval was from 3 to 5, the absolute min would still be the same. Okay, absolute min is still 1, attained at x equals 3 right here. But the absolute max, okay, would instead be 2. And if I said where does it attain that maximum value, it would be everywhere on the interval from 4 to 5. Okay, so be careful that you are talking about y values, not x values when we look at absolute extrema. For this next one, we have an algebraic function here. And again, we want to find any absolute extrema. So instead of graphing this function, we are going to use this list, okay, this list of three things, places where derivative equals 0, doesn't exist, or endpoints, to find our critical points. Okay, so let's go ahead and find the derivative using the power rule here. And then we're going to set this equal to 0. Now, mathematically, you don't have to write the word set over the equal sign, but I think that is very helpful for knowing when it is and is not okay to set something equal to 0, or to just put a 0 on the other side of the equation. I think that sometimes we are used to doing that, and then we end up doing it when it doesn't actually apply. So to avoid doing things algebraically without being mindful about them, I would recommend that you put set over the word equal, or over the equal sign, if you are setting something equal to 0. Okay, so we want to set this equal to 0. I'm going to divide everything by 3 to make this equation easier. So x squared minus 2x minus 3 equals 0. We can factor this as x minus 3 times x plus 1. So x equals 3 and 1. So when we list our critical points, okay, for part A here, from 0 to 4, we have x equals 0. Oh, sorry, this is a negative 1, not positive 1. Okay, 0, 3, and 4. So I'm doing endpoints of the interval. There's nowhere where this derivative doesn't exist because it's a polynomial. But negative 1 I'm leaving out here because it is not inside our interval. So then what we need is we need to know the value of the function f of x at each of these 3 points. And remember, value of the function, not value of the derivative. I already know that the derivative is 0 at the critical points, and I don't care about the derivative at the endpoints. So f of 0 is equal to 10. F of 3 is equal to 27 minus 27 minus 27 plus 10 is negative 17. And then f of 4 is 64 minus 48 minus 36 plus 10. So let's see, that's going to be 74 minus 80 minus 84, so that's negative 10. Okay, so our max is 10. It's the highest of the 3 values. So let me write this down here. Cheat a little bit. Absolute max is 10, and our absolute min is negative 17. For part B, okay, for part B, move this over a little bit. We already have the derivative. Okay, now we just need to consider the new critical points with the new intervals. So our critical points are now at x equals negative 1 and 3, because both of these are on this interval, okay, and 5, but also we actually do need to consider negative 5. Now remember, I said that critical, or places where extrema can occur, are endpoints on a closed interval, and negative 5 is not an endpoint on a closed interval, but we still need to consider what is happening, because if a function has a value at this point, if a function is continuous and differentiable, which this is, if it has a value at negative 5 that is either greater than or less than the values at the other critical points, it doesn't become the new max or min, but it disqualifies something else from being a max or min. Okay, so we do need to know the value of all of these. All right, so f of negative 1 is going to be negative 1 minus 3 plus 9 plus 10. Move this over a little bit. Make that a little bit bigger. Negative 1 minus 3 plus 9 plus 10. So that is 19 minus 4, whoops, which is 15. Okay, and then stop it. Okay, and then f of 3 we already computed, that's negative 17. F of 5 is going to be 125 minus 70, I don't know why that keeps moving, 75, here we go, try and fit that, minus 45 plus 10, which is 15, and then f of -5, which is -125 minus 75 plus 45 plus 10, which is -145. Okay, so our absolute max, occurs twice. All right, let me write this down here. And is 15. Okay, our absolute min is not -17, but it is also not -145. So the fact that this is lower than this tells us that there is no min on this closed interval, because we have something that's getting closer and closer and closer to -145 as x gets closer and closer to -5 from the right. Okay, but this -145, since it's less than -17, disqualifies the -17. So there is no min. Okay, there's no absolute min on that interval. All right, this question here says if f is continuous on the closed interval, then f has both extrema. Is this true or false? Okay, if a function is continuous on the closed interval, then does it have to have a max and a min? And the answer is yes. Okay, this is something that is guaranteed by the mean value theorem. Now, if you're trying to think about counterexamples to this, then the first thing that probably comes to mind is, what about a function that is just horizontal, has a constant function like this? Okay, and then we might say, well, if it's continuous on the closed interval from a to b, does it have both a max and a min if everything has the same height? The answer is still yes. This has both a max and a min value at whatever this height is. I'm just going to call this k. Or I shouldn't say at k, I should say of k. All right, so whatever that height is, by our definition, k is greater than or equal to every other value on this interval, and then also less than or equal to every other value on the interval. So the extreme value theorem is just this statement: if f is continuous on the closed interval, then f has both extrema. All right, one more example here using that extreme value theorem. It says, which of the following functions is guaranteed by the EVT to have an absolute max? So the only condition for having an absolute max on this interval is it has to be continuous. Okay, so is y continuous on the closed interval? That's all we need to consider here. So y equals tangent x. Is that continuous on the closed interval? No, it is not. Okay, y equals tangent inverse of x. Is that continuous on the closed interval? Yes, it is. Since the since the output of tangent is -infinity to +infinity, okay, thinking about a graph here, here's tangent, then the inverse of that has an input from negative to positive infinity, and actually looks kind of like this. Okay, so yes, this one is actually one that satisfies the EVT. So that's going to be our answer. Let's go ahead and consider the other two, though. This one right here, factoring, we would get x plus 4 times x minus 4 over x plus 5 times x minus 4. What is happening at x equals 4? We have a hole at x equals 4, meaning it is not continuous on the closed interval. So no, EVT does not apply. And then lastly, 1 over e to the x minus 1. This one, when e to the x minus 1 is equal to 0, if I set that equal to 0, e to the x equals 1 at x equals 0, which is the other endpoint, so it's not continuous at x equals 0, so not continuous on either endpoint.